Hey everyone, today we're going to talk about how to solve systems of linear equations. We'll set up some motivation. Suppose that we had two linear equations, each in the same two variables. In other words, suppose we have a system that looks something like this. Ax plus by equals c and dx plus ey equals f, where x and y are our variables and abc, def are our real numbers. This machine here is called a system of linear equations. The reason these equations are linear is because each variable is raised to a power of 1. First, let's talk about what it means to solve such a system. Given ax plus by equals c and dx plus ey equals f, the goal is to find values for x and y that satisfy this system. So if I found these values for x and y and plug them into the system, then I should get c and f in return. We have two systems here, so we essentially get three possible outcomes. We can either find exactly one solution, no solutions, or infinitely many solutions. You get exactly one of these three when you're solving a system of linear equations. Without going into heavy detail, the reason you get these three outcomes is because we have two equations and two variables. There are many ways of solving systems of linear equations, but the two methods that we'll use are called substitution and elimination. The main idea with solving a system of linear equations is letting the equations work together. So this means pulling information from one equation and plugging into the other, or just letting the equations interact with one another. Let's go ahead and get started on an example. Consider the system of linear equations 4x plus y equals 16 and 2x plus 3y equals 18. The goal is to let these systems work together, so what we're going to do for substitution is pick one equation. I'm going to pick 4x plus y equals 16, and I'm going to solve for one of the variables. In this case, I'm going to solve for y. When I do this, I get that y equals 16 minus 4x. This alone doesn't tell me much, except that I can write y in terms of x. What I'm going to do with this is take this information and plug it into the second equation. So I'm going to substitute y in this second equation for 16 minus 4x. When I do so, I get 2x plus 3 times 16 minus 4x. Once I simplify, I get 2x plus 48 minus 12x, and I simplify again to get 48 minus 10x. And since the equation I started with was equal to 18 in our original system, I get that 48 minus 10x is still equal to 18. So doing this, I have pulled information from one equation in my system, plugged it into the next, and now I have worked my way down to a single linear equation. When I solve 48x minus 10 equals to 18, I get that x is equal to 3. Now I'm going to take this value of x and plug it in for my expression of y that I found upstairs. So since we found that y equals 16 minus 4x, and then we found that x is equal to 3, we found that y is equal to 16 minus 4 times 3, which is equal to 4. Therefore, x equals 3 and y equals 4 is our solution set to this problem. This seems sort of like an ad hoc procedure. Substitution tells me to pick my first equation, solve for any variable that I choose, in this case I chose for y, and then I'm going to plug that information that I found on y into my second equation. Once I do that, it kind of narrows my scope so I only have one variable to worry about. And then I can solve that variable explicitly, and I get x equals 3. And since I found that y was written in terms of x, I can plug this x value in and then get a solid expression for y as well. And that's really the layout of how substitution works. First, I solve for any variable that I choose, which I did. Second, I substitute it into the other equation. And then third, I get a value for one variable, and then I use that information to get the value of my other variable. It does feel like this back and forth process, but this is what I mean by letting my equations work together in this system. As an exercise, you might want to start with this system and solve for x first instead of y. If you go through these same kinds of steps, you'll end up with the same system of x equals 3 and y equals 4. You might have to work with fractions if you do this, but I guarantee that you'll end up with the same system. For our next example, consider the system 3x plus 5y equals 9 and 2x plus 3y equals 4. And to solve this, we'll be using the method of elimination. To use elimination, we'll run through the steps. First, pick a variable. So for us, we'll just start with x. Second, find the least common multiple of the coefficients of the variable that we just chose. Since we chose x, our coefficients are 3 and 2, which have a least common multiple of 6. For the third step, we're going to multiply both equations by appropriate numbers so that the least common multiple we just found is present in both systems. For us, since our least common multiple is 6, we're going to multiply the top equation by 2 and the bottom equation by 3. The reason we're doing this is because multiplying 2n will give me a 6x, and multiplying 3 into the second equation will also give me a 6x. The point is we want the coefficients of the variable we chose, x, to match. This is similar to the idea of finding a common denominator when you're adding fractions. For the last step, we subtract and solve. In other words, we subtract the equations from one another. So after I multiply both systems by the 2 and 3 respectively, I get the new system of 6x plus 10y equals 18 and 6s plus 9y equals 12. Again, I got exactly what I wanted, which is for my coefficients of x to match in this revised system. The next step is to subtract these from one another. And since my coefficients of x match, what's going to happen is my 6x's are going to cancel. They cancel, and I'm left behind with 10y minus 9y, which is y, and 18 minus 12, which is 6. It turns out that this is all the work I have to do because this subtraction revealed my solution for y. Now that I have this information on y, I can plug this value in for y to any equation upstairs that I want to get my value for x. So I'll choose 3x plus 5y equals 9. Substituting y in for 6, I get 3x plus 5 times 6 equals 9, which simplifies down to x equals negative 7. Therefore, I get a final solution set of x equals negative 7 and y equals 6. And that's how elimination works. So just to recap the problem, the first thing I did was pick a variable. I picked x. And then I looked at the coefficients of x. I want these coefficients to match, so I figure out what their least common multiple is, in our case it's 6, and then I multiplied the top and bottom equation by numbers so that when I'm done, I get 6 in both places. And then once I subtract, the 6x's cancel, and it leaves me just with y. So I let the equations work together so that I'm down to exactly one variable. Just like before I narrowed the scope, I can solve for one variable, and then with that information, use it to find out about the second variable. For our last example, consider the system x minus 2y equals 3 and 2x minus 4y equals 7. I'll proceed by using substitution, and I'll use the first equation and solve for x. When I solve for x, I get that x is equal to 3 plus 2y. Now I plug this value for x into my equation below. So 2x minus 4y equals 7 becomes 2 times 3 plus 2y minus 4y equals 7. I carry out a round of simplification to get that 6 plus 4y minus 4y is equal to 7, which brings me down to 6 equals 7. And that's a problem, because clearly 6 does not equal 7. So none of the math that we actually did was incorrect. Every step that we took was accurate, but we still landed at a statement that's just not true. So what that actually is telling us is that this system of linear equations does not have a solution. We said on one of the earlier slides that that could happen, and this is an example of when that happens. When you have an inconsistent system, sometimes you land at statements like this, where numbers equal other numbers.